Hello everyone. So in this lecture we will be discussing about the DP optimization onto the previous recursive algorithm. First going on to the DP optimization, I just want to discuss one more thing with you. Look, the same way as we did in our knapsack problem, we can again implement this same recursive algorithm which we have implemented in the previous lecture by starting from the last index. So we will have a quick review that what are we actually doing over here. So we will make use of the same algorithm to build our tabulation method as well. So what do we see over here? This is again the method which is returning the total number of ways we can make a change of 4. But here we are starting with the index 2 or the last index. So what do I do? If I choose to use this index or the denomination present at this index, so what would I be left with? I would be left with only 1 over here. My leftover change is 1 because I had a denomination of 3 at this index. And if I do not choose it, then what would I be left with? I would be left with all of my denominations, but I would be decrementing my index. And what does this say? This says, okay, now starting from 0th index till this element, just tell me in how many ways can I make a change of 4. And what does this subproblem mean? This subproblem means that, okay, just tell me starting from index 0 to this index, in how many ways can I make a change of 1. So again, if I choose to make use of the denomination present at this index, then what would I be left with? I would be left with negative amount, because what is the denomination which I am having at this index? It's 3. And what is the leftover change? It's 1. So if I make use of this denomination 3, then what is the amount I would be left with? I would be left with minus 2, because I would be subtracting 3 from this leftover amount. So I cannot go, or I cannot recurse further on this path, because I can never make a sum of some positive integers which will result to me in a negative integer. Hence I will be returning 0 over here. So this path is now totally unusable. I won't be recursing further in this path. But if I do not make use of this denomination present in this index, then what would I be left with? I would be left with coin 1 comma 1. So what does this subproblem mean? That starting from index 0 till this index, just tell me in how many ways can I make a change of 1. So if I choose to use the denomination present at this index, then what would I be left with? I would be left with again a negative denomination, a negative amount to make. So I would be again returning 0 over here. But if I do not choose it, then what would I be left with? I would be left with all of my amount, but I would be left with one less denomination. So what does this subproblem mean? This subproblem means that currently I am sitting at index 0. So just tell me, by making use of this index 0, because it's my first index. So by making use of this index, in how many ways can I make a change of 1? So what would I be doing? If I make use of this denomination present at this index, so what would I be left with? I would be left with coin 0 comma 0. And if I do not choose it, then I would be left with coin 1 comma minus 1. So before going on to 0 comma 0, we can discuss over here. This is again a base case. And why is this a base case? Because do we have anything as index minus 1 in our array? Or what does this minus 1 actually specify? This minus 1 specifies that I have no denomination left with me now, but I am still left with some amount to make. So can you ever make some amount and you do not have even a single denomination with you, or you do not have even a single coin with you? No, you cannot make it. You need some coins to make some amount. Hence I would be returning 0 again from this recursive call. And coming on to this recursive call returns 1. Why does it returns 1? It returns 1 because now my amount over here is 0. And how did I reach this 0? I would have reached this 0 only when I would have made use of some denominations and I have already got my amount, and hence I would have reached 0 over here. So I would be returning 1 from this recursive call. So which all denominations did I make use of? I made use of 3. I did not make use of denomination 2. Then I made use of denomination 1. I am talking about this path. I made use of denomination 3 and I made use of denomination 1. So can you see what are the base cases in over here? So if we make use of the denomination, then we would be subtracting the value of the denomination from the leftover change and recursing for the same number of denominations. But if I do not choose it, then what would I be left with? I would be left with the same amount in the subsequent recursive call, but I would be recursing for the remaining elements. So keep this in mind, and now we will move on to our DP optimization. So now coming on to the DP matrix, what are these columns and what are these rows? These columns specify the amount which we need to make and the intermediary amounts which are basically used for recursing. So if we go to this part of the recursive tree, what do we see over here? What were we actually recursing for? We were recursing for amount of 4. If I make use of this denomination, then I will be making use of amount of 1, and again amount of 4, amount of 1. So the same way, if you would have made use of this amount, this denomination, then somewhere in the recursive tree you will again be left with an amount of 3. So these are all columns specify that thing, the leftover amounts and the intended amount to make. And what are these? These are the denominations which we are making use of. Look, this is the same array which I have listed over here. Now we will start filling our base cases, then we will go on to our sub problems until unless we reach our intended problem. So coming on to the first base case, what does this means? This means that I am not left now even with a single amount over here. Look, I am talking about this base case. Am I left with even a single amount? No, I have reached 0 over here. And what does this 0 mean? This 0 means that I am not left anything in my amount because I have already made it. So now coming on to this sub problem. So what will we do? If we have 0 amount to make, so even if you are having any number of denominations, so what do you need to recurse further? No, you need not recurse further. Why? Because you have already made the amount which you were actually intending to make. That's why you would have reached 0 over here. So the answer to this sub problem would be 1. And what does this one signify? This one signifies yes. This is my leaf node actually, the base case I am talking about. These are on my leaf nodes. So I am returning 1 from this. And what does this one signify? This one signifies yes, this path will result in a way with which I can make an amount 4. This one signifies that thing. Look, this is the path which I am talking about. So this one signifies that the path which I have taken from my root node to this leaf node results in a 1. And why 1? Because with the help of this path or what all denomination I have used during coming on to this path, I have made an amount of 4. And hence I would be returning 1 over here. The answer to sub problem 0, 0 would be 1. What about this sub problem? When you have a single coin of one denomination but your leftover amount is already 0, again the answer would be 1. The answer to this sub problem would also be 1. The answer to this sub problem would also be 1. Now coming on to the first row over here, my first column would all be 1. If you didn't understand it, please rewind the video and have a look into it, that why are we actually populating 1 over here. Each and every matrix cell is actually a sub problem in itself. Currently we are filling all the leaves of our recursive tree, and those leaves are actually base cases. Now what does first row signify? This first row says that you do not have even a single denomination left with you, but you have still some amount left with you to make. Now what does this sub problem say? This sub problem say that what is the amount which you are left to make? You are still left with 1 over here, but you do not have any denominations left with you. And what was this base case in this tree? Look, it was this base case. I have some amount left to make, but I have no denominations left with me. How did I reach -1 over here? I only reached -1 only when I have made use of all the denominations, or I have decided on all the denominations. So I am coming to -1 over here. It doesn't mean that I have made use of all the denominations. It just says that I made decisions on each and every denomination, but I am still left with an amount of 1, but I have no denominations left with me. So can you ever make an amount when you do not have even a single denomination left with you? No, you cannot make it, and hence I will be returning 0. What does this 0 signify? This 0 signifies that the path or the way which we took from our root node to this leaf node, I am talking about this path, this does not result in a way to make an amount 4. This 0 signifies that thing. I highly recommend you to just branch out for each and every recursive subproblem over here and make the distinction with the previous recursive tree. So you will come to know how we are actually populating our DP matrix. So what do we see? We would be returning 0 when I am out of bounds or I do not have even a single denomination left with me. So coming on to this subproblem, what does this mean? This means that I still have amount of 1 to make, but I have 0 denominations left with me. So what would be the answer to this subproblem? It would be 0. So what does this subproblem mean? The intersection of this 2 and this 0. This says that I am still left with the amount of 2 to make, but I do not have even a single denomination with me. So the answer to this subproblem would again be 0. The answer to this subproblem would again be 0. The answer to this subproblem would again be 0. So I think you would have understood that how are we actually populating our base cases. So these are actually the leaf nodes which I am talking about. So now coming on to the code, how do we actually do it? If I just comment the population of our whole DP matrix over here, we can have a look that how do we actually populate our base cases in here. What do we see over here? What does this mean? This means that I am at my 0th column and in first row. So what I was doing over here, what does this signify? That I am at my 0th column and first row, 0th column second row, 0th column third row, 0th column fourth row. So what was the answer to all these base cases? It was 1. Why it was 1? Again, we have discussed it earlier. Now what about this base case? This base case says that I am at 0th row but first column, 0th row second column, 0th row third column, 0th row fourth column. So what was the answer to my 0th row? My answer to 0th row was 0. Again, we have discussed it previously. Why the answer to my 0th row is 0 and why the answer to my 0th column is 1 over here. So I hope you would have understood. Now let's see that whether we have populated our DP contents correctly or not. So what shall we see? Yes, we can see over here. What do we have? In our 0th row, except the element 0 0, we have all zeros, and in my first column or my 0th column, the answer to those subproblems is 1 over here. Now we will proceed that how do we actually populate our remaining DP matrix. So if we come to this subproblem, what does this say? This says that I have an amount 1 to make and I have a denomination 1 with me. So just tell me in how many number of ways can I make a denomination or can I make an amount of 1 with the help of one denomination. So I can do two things. I can either include the denomination present over here or this one, or either I can exclude it. So if I include it, then what I was doing actually in my recursive algorithm, I was just saying, okay, I have included the element. So the first thing I would be doing is I would be subtracting the value of the denomination from the leftover amount. So I would be left with 0 sum now, but I would be making use of the same index, or I would be making use of the same denomination again. So if we see in the recursive tree, what did we do actually? Look, currently I am at index 2 and I have a amount 4 to make. So if we make use of the denomination present at this index, so what I was doing, I was subtracting the value of the denomination from the amount and I would be left with 1, but I was not decrementing my index. I was just saying, okay, now just tell me with the use of same index, can I again make use of the amount or the leftover amount or not? That's what I have done over here. I have made use of the denomination and hence I am left with an amount 0 to make, but with the same index again. But if I exclude this item, then what would I be left with? If I exclude this item, then what is the amount which is still to be made? It's 1. But I would be recursing for the same amount in the remaining elements. So where can I find this subproblem? 1, 0, it's 1, 0. So the answer to this subproblem is 1. The answer to this subproblem is 1. And if I see over here, where can I find this subproblem? I can find it over here. The answer to this subproblem is 0. So what we were doing, now we need to add them. That's what we were doing now, to find the total number of ways with which we can make this amount. So I would be doing 1 plus 0 and the answer to this subproblem would be 1. And hence with the same way I will be populating my rest of the DP matrix. If you want to see this one, then we can have a look into it. What does this subproblem mean? This subproblem means this, I am left with an amount of 2 to make and I have a denomination of 1. So in how many ways can I make it? So if I try to include this element or include this denomination, so how much amount would I be left with? I would be left with an amount of 1, but I would be recursing for the same number of elements. But if I do not make use of this denomination or I exclude this denomination, so how much amount would I be left with? I would be left with the same amount, but I would be left with remaining elements. So where can I find 1, 1? It's over here, 1, 1. So answer to this subproblem is 1. And where can I find 0, 2? The answer to 0, 2 subproblem is 0. So the answer is 0. So again I would be adding it. So the answer to my subproblem 1, 2, or where the amount left over is 2 and I have a denomination of 1, the answer to that subproblem is 1. So what does this one signify? This one signifies that the total number of ways with which I can make an amount of 2 with the denomination of 1, or by making use of the denomination 1 is 1. There is only a single way with me. So we will be making use of this reconciliation to build our DP table. But there is one more thing to notice over here. Now suppose you do have a denomination of 2, but the leftover amount you need to make is only 1. So what would you be doing over here? If you try to include this element or include this denomination, then what is the leftover amount, or what would you be left with over here? You would be left with an amount of -1 to make, and you would be recursing for the same index over here. But if you exclude the element, so what would you be doing? You would be saying, okay, I am left with all of my amount, but I wouldn't be making use of this index. Just tell me in how many ways can I make the same amount with the remaining elements. So do you have such kind of subproblem in your matrix? No, you do not have it. So, and the answer to this is, first of all, it would be 0. What does this -1 mean? This -1 means that now the amount which I need to make is negative, and you can no way create a negative integer by adding some positive integers, and hence that's what we did over here. Can you make an amount of -2? No, I was returning a 0 over here. Can you make an amount of -1? No, I was returning a 0 over here. So the same way, the answer to this subproblem is 0. So whatever you do, if you add these both items, so will this even matter? The answer to this subproblem would be the answer to this subproblem, because if I return 0 over here, so whatever might be the answer to this one, it's the answer to coin 1, 2 is totally dependent of the subproblem where I exclude the coin or exclude the denomination. So my answer would totally be dependent on excluding. So in this case, I must exclude the coin. And why am I excluding? Because the value of my denomination is greater than the amount which I need to make. So I need to exclude this denomination and recurse for the remaining denominations with the same amount. So where can I find this subproblem 1, 2 over here? I can find it over here, and the answer to that subproblem is 1. So 1 plus 0 is 1. So can you see my answer is only dependent on the subproblem where I exclude the current denomination. So the answer to this subproblem would also be 1. So in such scenarios, what I would be doing, where the denomination which I have in my hand is actually more than the amount which I need to make, so I would be excluding that. My answer will be dependent on only the recursive call where I have excluded the denomination, and in other cases I will try to branch out. So that's what we have done in this recursive tree as well. In this case, as we know, if my denomination, what is present at this index, the denomination present is 3, and what is the amount which I need to make, it's 1. As this 3 is greater than 1, so my answer will be only dependent on coin 1, 1, because whatever be the answer to this thing, that would be the answer to this thing, because adding a 0 doesn't make a difference to me. Hence I have applied the same thing in my recursive, this DP table. I highly recommend you to that please rewind the video if you didn't understand this logic over here. So now coming on to the code, how do we actually do it? What do we do is that, again, I will be making a check once, that what does J represent? J is the column, and my column represents the amount which I need to make. So if it's less than the denomination which I am currently holding in my hand, so what would be the answer? I would be recursing for the remaining denominations with the same amount. That's what I was doing over here. I would be, if we see in this recursive tree, what would I be recursing for? If my denomination at this index is greater than the amount to make, I would be recursing for the remaining elements with the same amount. I am recursing for the same amount 1, but in the remaining elements. That's why I have chosen 1 over here. I have deducted an index over here. So I have excluded in other way. So that's what I am doing over here. I will exclude the current denomination, and that would be my answer to the current subproblem. But if the amount which I am holding is greater than the denomination which currently I have, so in that case I will be branching out. What does this branch mean? This branch means to exclude the item, and this branch means to include the item. So this will give me the answer, the number of ways with which I can make the coin if I include the denomination currently I have. And what will this give? This will give me the number of ways in which I can make the current amount if I exclude the item. So if we see the contents over here, I think I need to change this. Yes, I need to make an amount of 4 over here. So if we see the contents, what do we see? Yes, what does this 4 signify? What is this subproblem in the matrix? The intersection of this 4 and this 3. This is my intended problem. What does this say? That I need to make an amount of 4 and I have an array of 3 denominations with me. So this is the answer to this subproblem, or the last matrix cell actually signifies the answer to my original problem. So the answer to this subproblem is 4 over here. We can easily see over here. So this is the way in which we have applied our tabulation method to our recursive algorithm. So in the next video or in the next lecture, we will look into another DP problem. So meet you in the next lecture. Till then, thank you.